Hello, in today's video we're going to explore gravitational potential energy. Have you ever lifted a rock into the air and then let it go down? It falls, right? But but before you drop it, it seems like you're storing energy just by holding it up. That's because raising a rock gives it gravitational potential energy. The energy it has due to the position. In this video, we will break apart what it means and why it's important. Let's let's start by imagining a box that's ready to fall down. So we'll have our box right here, and the box has a mass m. That's what we're going to represent m1, and it starts from this position y1, and it ends up in this final position when it moves down as it falls, and we'll call this one y2. And let's make that a better one right here so you can see what we're looking at. Now, from the image, we notice that the gravitational force, which is pulling on this object, is represented just as mg. And these are the directions of the y from here. And the difference is going to be y1 minus y2. And this force that we're looking at is in the direction of displacement, which kind of makes our problem a little bit easier. So we're gonna find that the work that this thing is doing, this crate, is equal to force times displacement. So we know our displacement, that's y1 minus y2. Now what is our force? We know that's mg, and the angle between these two is just cosine of 0, which is 1, so it's omitted in this example here, as it's not necessary. So we'll plug in mg times our displacement of y1 minus y2. Right now we're deriving how we find our gravitational energy. So now you have to distribute the mass times acceleration. So we have mass times acceleration of y1 minus the mass times acceleration times y2. And then we can just write this. I mean, that's pretty much the final form right here for the moment. This formula tells us how gravitational force does work on the box as it falls from one position right here to to the bottom position. This leads us to the idea that weight and height above the ground are related to gravitational potential energy, and we donate this as W for potential, and then we'll write just G just to make it shorter. You can write grav if you want to be explicit. So the potential energy is equal to the mass times, and we can write Y, but often you'll see in problems it will be represented of H. So whatever the height that it changes, that's that's how you would write it right here. Now we'll move on to a different case where we have a box which is on the ground and it moves up into the air. So we'll have to redraw our picture real quick here. So this is your y1, and it's gonna go up to here, and this is y2. And if you already know it, it's really just the inverse of what we were looking at before. So we're gonna save ourselves some time by writing the work of the potential energy of gravity is equal to minus, and we'll write ug1 for this is where y1's at, minus UG2. This is going to include the Y2. And as you can see, it's really just the inverse. So we'll write it, our answer as, we'll write the inverse as UG2 minus UG1. And I guess you can kind of get the idea by looking at this, as the object is its final potential energy is gonna be greater than the initial, since we moved the object upwards. Previously it was negative, since the potential energy is less than it was before. It's just a change of signs, and we can write this as, this is just the negative sign of the displacement of the potential energy is equal to the work of gravitational potential energy. This equation shows us that gravitational potential energy increases when an object moves upward and then decreases when the object moves downward. Finally, since that the potential energy is equal to mgh, we can see that the unit is measured in joules, and we'll show that here. So we have the potential energy G is equal to mgh, which is really kilograms times meters over second squared times meters, which equals kilograms times meters squared over second squared, which is our familiar joules. As you would expect, because we're finding the work of gravity, we know that the units for work is also known as joules in our example here. Now let's move on to a practice problem where we can implement this quick idea that we just introduced you. So let's say that you held up a rock right here 5 meters above the ground. Wait, 5 meters, and the rock weighs 2 kilograms. Now the question asks, what is the gravitational potential energy of the rock has? And we remembered from our gravitational potential energy thing here, it is equal to mass times g and then h, and which will represent the height that it's going to fall down, which is equal to 2 kilograms times 9.8 meters squared times 5 meters. And as we can see, this will be as kilograms as you'd expect. You can really just, if you want to make this quicker, just make this 10 times 10, which is going to be 100. But because we want to be accurate for numbers, we're going to write it as 98. So you'd have 98 joules instead of 100, which can be important to get those numbers exact. And thank you for watching my video today. I hope that you learned something, and don't forget to like and subscribe if you enjoyed watching my video today.